Hello, all. Welcome to the session. Myself, Dr. Murugan P., Assistant Professor, Department of Mathematics, Madanapalle Institute of Technology and Science, Andhra Pradesh. So, today's session we are going to discuss about finding the eigenvalues and eigenvector of 3 by 3 matrices. So, first, this is the outline of the today presentation. We'll start with the first definition of eigenvalue and eigenvector. Next we go for the process of finding eigenvalues and eigenvectors. Next we will see some examples. So there are three type of examples. The first one is if all the eigenvalues are different, and second one is when when two of the eigenvalues are same, and the last one is if all the eigenvalues are repeated. So we'll see these three type of examples for 3 cross 3 matrices. So first we'll start with the definition of eigenvalue and eigenvector. Let A be any n cross n square matrix and a non-zero vector x is a eigenvector of a matrix A if there exists a scalar lambda such that Ax equal to lambda x or A minus lambda I into x equal to 0, where lambda is a eigenvalue of corresponding eigenvector x and x is not, I is nothing but the identity matrices with same size of A. So why we are taking n cross n matrices here, we will discuss about that one later. So we can ask any question about why we are taking the n cross n square matrices here. So instead of taking any other size of matrices, that will be why, because in the process we can see that one. So the process of finding eigenvalue eigenvector, the firstly we need to find a characteristic polynomial. The characteristic polynomial is nothing but determinant of a minus lambda I. So before going to determinant of a minus lambda I, we need to form a matrices a minus lambda I. Next we can take a determinant of a minus lambda I, where lambda is eigenvalue eigenvalue corresponding to x. Then I is nothing but the identity matrix of same size of A. So the determinant of A minus lambda is nothing but a polynomial. It will be polynomial in the variable of lambda. So if you are, suppose if you are taking 3 cross 3 matrices, you will get a cubic polynomial. If 2 cross 2 matrices, that will be a quadratic polynomial. For 4 cross 4 matrices, that will be a fourth degree polynomial. So the next we need to compute a characteristic equation. The characteristic equation nothing but a characteristic polynomial equal to 0. By solving the characteristic equation, we will get our required eigenvalues. If A is a n cross n matrix, then we will get n eigenvalues. So maybe the eigenvalues will be same or different. The possible eigenvalue are 0 also possible eigenvalues. So to find eigenvector, first we need to back substitute the lambda into a minus lambda I. After that, using the definition of eigenvalue and eigenvector, we can find eigenvector. So next we move to the example section. So if all the eigenvalues are different, we can see one example for that one. So first consider the matrix A. The first row will be 3 minus 4 plus 4. The second row is 1 minus 2 4, and the third row is 1 minus 1 3. So to find eigenvalue, first we need to find a characteristic polynomial. To find a characteristic polynomial, first we need to form a matrix A minus lambda I. So the A minus lambda I is nothing but matrix A minus lambda into identity matrix. That means we need to minus lambda from the diagonal elements of A. So that is what here presented. So next we need to compute a determinant of A minus lambda I. The determinant of A minus lambda I. So next we are going to take a determinant of the 2 cross 2 submatrix 1 4 3, the 1 3 minus lambda. So that taking determinant of 2 cross 2 matrix is nothing but product of, so here product of main diagonal. That means this one equal to 1 into 3 minus lambda minus 1 into 3 minus lambda. So 1 into 3 minus lambda minus 4 into 1. So that is nothing but 3 minus lambda minus 4. So that means minus lambda minus 1. So next we find the determinant of 2 cross 2 submatrix 1 minus 2 minus lambda 1 minus lambda. Same. So product of main diagonal minus product of anti-diagonal. After simplification we'll get lambda plus 1. So now what we are going to do is we are going to back substitute those values into this determinant. So after back substituting, we will get 3 minus lambda into lambda square minus lambda minus 2. This is the value of that 2 cross 2 submatrix minus lambda into lambda plus 1 plus 4 into lambda plus 1. So this minus quantity and this plus quantity will get cancelled. So the remaining will be 3 minus lambda into lambda square minus lambda minus 2. So first multiply 3 inside and after that take a minus lambda and multiply inside. So after simplification we will get this polynomial. This is nothing but our characteristic polynomial 3 degrees. So we took 3 cross 3 matrices. Though we are getting 3 cross 3 polynomial. So this is nothing but our characteristic polynomial. If you are giving this polynomial equal to 0, that is nothing but our characteristic equation. To get eigenvalue, we need to find root of this characteristic equation. To find the characteristic root of this characteristic equation, first take the coefficient of this characteristic equation. So 1 minus 4 1 6. So put this L shape. So first put 0 here and here we need to get minus 6. So accordingly we need to give value here. So the eigenvalue is nothing but a root of this equation. So that means the root will be divisors of this 6. So what are the divisors of 6 is plus or minus 1 and plus or minus 2 and plus or minus 3. So these are the values which will be possibly our root of this equation. So start with plus 1. If we are putting plus 1 here 1 1 1 into 1 1. So minus 3 will get. So first we are putting plus 1 will get. So 1 plus 0 1. So 1 plus 0 is 1. So 1 into 1 is 1. So minus 4 plus 1 is minus 3. So 1 into minus 3 is minus 3. So 1 minus 3 will be minus 2. So 1 into minus 2 will be minus 2. It's not a minus 6. So that means plus 1 is not a value. So minus 1 is the possible. So next we put minus 1. So 1 into minus 1 is minus 1. So minus 4 minus 1 is nothing but minus 5. So next minus 1 into minus 5 is here plus 5. So 1 plus 5 nothing but, so 1 into so 1 plus 5 is nothing but 6. So minus 1 into 6 will be minus 6. So this is the possible. So likewise we can put lambda equal to 2 and lambda equal to 3 and we'll get these are the eigenvalues. After using this form we can get it, these eigenvalues. So these are our required eigenvalues. We are going to find eigenvector for this eigenvalues. So before going into that, first let us consider this column vector x be an eigenvector corresponding to lambda. So by the definition, a minus lambda I into x equal to 0. So here put a and lambda into I into x. So the a minus lambda is nothing but 3 minus lambda minus 4 4 1 minus 2 minus lambda 4 1 minus 1 3 minus lambda into the column vector x1 x2 x3 equal to 0. So this is our equation 1. So now what we are going to do is we are going to find corresponding eigenvector for lambda equal to minus 1. So first substitute lambda equal to minus 1 in the above equation. So 3 minus into minus 1 is 4. So that means So now what we are going to is we are going to find eigenvector for lambda equal to minus 1. So to find eigenvalue for lambda equal to minus 1, we need to put minus 1 in for lambda in the definition. So already we have the matrix 3 minus lambda minus 4 plus 4 1 minus 1 minus 1 minus lambda 4 1 minus 1 4. So this is nothing but a minus lambda I. So in this we are going to put lambda equal to minus 1. If we are putting lambda equal to minus 1 here, we will get 3 minus minus 1, that will be 3 plus 1, that will be 4, and minus 1 minus of minus 1 will be minus 1, sorry, here plus 1. So 1 minus minus of minus 1, sorry, here I think this is minus 2 minus lambda, so that will be minus 2 minus of minus 1, that is minus 1 4 1 minus 1. Here we will get, we have same 3 minus lambda, that will be minus of minus, that will get 4. So after multiplying the first row with this column vector, we'll get 4x1 minus 4x2 plus 4x3 equal to 0. So take a second row and multiply with the column vector, we'll get x1 minus x2 plus 4x3 equal to 0. And take a third row vector and multiply with this column vector, we'll get x1 minus x2 plus 4x3 equal to 0. So we'll get these three equations. The value of x1, x2, x3 is our required eigenvector value. So to find that x1, x2, x3, we need to solve these three equations. Okay, to solve these three equations, I'm going to use the method of cross multiplication. So to use the method of cross multiplication for three variable equation, we need to get two distinct non-zero equation. So non-zero equation, so that means here these two are the non-zero equations. So I'm going to take these two non-zero equation and I'm going to find cross multiplication. To find cross multiplication, so first put x1, so here x2, and this is x3. So start with the coefficient of x2, so minus 4, next coefficient of x3 plus 4, and the coefficient of x1 4, and end with the same coefficient minus 4. So next the second equation, start with the coefficient of x2, that is minus 1 4 1 minus 4. So this is the cross multiplication. So the x1 value will be the cross product of this equation. That means the determinant of this one will be, the 2 cross 2 is our x1 value. So the determinant of this 4 value will be our x2 value. The determinant of this 4 value will be our x3 value. See here. So we are having that thing. So the determinant of this value is x1 value, and determinant of this equation value will be our x2 value, and determinant of this one is our x3 value. So the determinant is nothing but multiple of main diagonal minus multiple of opposite diagonal. So 4 into 4 will be 4 into minus 4 is minus 16. So minus of minus 1 into minus 4 minus 4. So minus 16 minus 4 will be minus 16 plus 4 is nothing but minus 12. So here 4 minus 16, the x2 value will be 4 minus 16 is minus 2, here minus 4. So if you are multiplying crossly, so minus 4 minus of minus 4 will be 0. So take out the common factor out, the remaining will be, so this one also we can say as our eigenvector. So but more simply we will take a common factor out, the remaining value will be our corresponding eigenvalue. So this is eigenvalue for lambda equal to minus 1. So our next eigenvalue is lambda equal to 2. So for that we are going to find same. So first put a lambda value into A minus lambda I matrices, we will get this matrices. So after that, product the row value with the column vector, we'll get this three equation. So solve this to solving this three equation, we will get our corresponding eigenvector. To solve this three equation, we are going to use as usual the method of cross multiplication. To use method of cross multiplication, we need two non-zero equation. So for that, I'm going to consider this two non-zero non-zero equation for solving this equation. To solve this non-zero equation using cross multiplication, first write x1, x2 and x3. So start with the coefficient of x2 from the first equation. So that is minus 4. Second x3 coefficient. Next x1 coefficient is plus 1 and end with the same coefficient, that is minus 4. So second equation will be minus 1, 1, 1, minus 1. So where you are starting coefficient, that one you need to enter. So to find value of this one, we need to take a determinant of this one. This one will be eigenvector of value of x1. If we take the determinant of this matrix, we will get value of x2. If we take this 4 value determinant, we will get x3 value. See here. So x1 will be determinant of this one, x2 value will be determinant of this one, x3 value will be determinant of this one. So already we know that. So the finding 2 cross 2 determinant will be product of main diagonal minus product of opposite diagonal. So that is here minus 4 minus of minus 4. So that will be minus 4 plus 4 0. So here 4 minus 1 3. So say minus 1 minus of minus 4 is plus 4 3. So to take the common factor 3 out, the remaining will be our eigenvector. So our corresponding eigenvector for lambda equal to 2 is 0 1 1. So next we will find eigenvector for lambda equal to 3. Sorry, here 3. So find eigenvector for lambda 3. We need to substitute lambda value into A minus lambda I into x equal to 0. So after substituting lambda value here, A value and I value in the one equation, we'll get this matrix. So after that, take a cross product of this first row and column vector, we'll get 0x1 minus 4x2 plus 4x3 equal to 0. So take second row and multiply with the column vector, we'll get x1 minus 5x2 plus 4x3 equal to 0. And take this third row, x1 minus x2 plus 0 into x3 equal to 0. So to find the solution of this three equation, we are going to use same as method of cross multiplication. To use method of cross multiplication, we need to take any two distinct non-zero equation. So if we consider this one and this one, that will be easy. So start same x1, x2, x3, and the value we need to start. So I'm going to take these two equation. The first equation coefficient of x2 is minus 4. The coefficient of x3 is 4. And the coefficient of x1 is 0 and end with the coefficient of x2. Similarly for the equation, second equation. So the coefficient of x2 is minus 1 and the coefficient of x3 is 0 and the coefficient of x1 is 1 and the coefficient of x2 is minus 1. So if you're taking determinant of this matrices, we'll get x1 value. If you take determinant of this matrix, we'll get x2 value. If you take determinant of this matrix, we'll get x3 value. So see here, this is x1 determinant, x2 determinant and x3 determinant. So determinant of this 2 cross 2 matrix is nothing but product of main diagonal and product of minus product of subdiagonal. So 0 into minus 4 is 0, minus of minus 4, that will be plus 4. So here 4 minus 0 4 and minus 1 into 0 is 0. So minus of minus 4 is 4. So take common value out, we'll get 1 1 1. This is our corresponding eigenvector for lambda equal to 3. So for this matrices, we are having three distinct eigenvalues. So for the three distinct eigenvalues, we are getting three different eigenvectors. So this is the linearly independent eigenvector for corresponding eigenvalues. So next, we are going to find eigenvectors for if what I will find if two eigenvalues are same. For that, we are going to consider this matrices as an example. So consider this matrix. To first, we are going to find eigenvalue. To find eigenvalue, we need to form a minus lambda I matrix. So a minus lambda I matrix is nothing but if you minus from the lambda from the main diagonal, that will be a minus lambda I matrices. So that means a matrices minus lambda into identity matrices. So I is nothing but 1 0 0 0 1 0 0 0 1. So this is a 3 cross 3 identity matrices. So product lambda here, that will be lambda I. So minus lambda I. So a minus lambda I is nothing but this one. So to compute, we need to find characteristic polynomial, we need to compute determinant of this matrices. So determinant of this matrix, we are going to expand along with the first row. So this one is plus, this one is minus, and this one is plus. So before going to finding determinant, we need to consider these symbols. So plus into this one, minus into this first row second element, plus into third first row third element. So after expanding along with the first row, we'll get minus to minus lambda. That means we need to consider first row first element, delete the first row and corresponding column, we'll get 2 cross 2 submatrices. So we are going to find, so the determinant of this 2 column. So minus into 2, that will be minus 2, and delete corresponding row and corresponding column, we'll get this 2 cross 2 submatrices. So at last 3. So minus 3 into corresponding row, delete corresponding row and corresponding column, we'll get this 2 cross 2 matrices. So next we need the value of this determinant. So we are taking this determinant out, we are going to find value of this determinant. So that is nothing but product of main diagonal minus product of opposite diagonal. So 1 minus lambda into minus lambda minus of minus 6 into minus 2. That will be minus lambda plus lambda square. So minus into minus plus, plus into minus, minus 12. So this is this one. So next, find determinant of this 2 cross 2 matrices. That is product of main diagonal minus product of opposite diagonal. So that is minus 2 lambda. So 3 minus the product of 3 minus is again minus 6. We'll get this value. So next we find determinant of this 2 cross 2 submatrices. That is product of main diagonal minus product of opposite diagonal. We'll get minus 3 minus lambda. So back substitute those 2 cross 2 submatrices determinant into our determinant of a minus lambda I. We'll get this one. So after expanding and simplifying, we'll get this 3 third degree polynomial. So why we are getting here third degree polynomials? We are taking 3 cross 3 matrices. So for 3 cross 3 matrices, we need to get cubic polynomial as a characteristic polynomial. So this is nothing but our characteristic polynomial. So for 2 cross 2 matrices, you will get quadratic polynomial. For 4 cross 4 matrices, you will get fourth degree characteristic polynomial. So if you give this characteristic polynomial equal to 0, that will be characteristic equation. So next we need to find root of the characteristic equation. So as usual, take the coefficient of the characteristic equation. So that will be 1, 1 minus 21 minus 45. So put L. So here 0. Here we need to get plus 45. So the first possible value is minus 3. If we are getting minus 3 here, so this is 1 plus 0 is 1. So minus 3 into 1 will get minus 3. So 1 minus 3 is nothing but minus 2. So minus 3 into minus 2 is nothing but plus 6. So 21 minus 6. So that is, so what is the value of 21 minus 6? So what is the value of 21 minus 6? So 21 minus 6 is 15. minus 15. So 3 minus 3 into minus 15 is nothing but plus 45, that is 0. So that means minus 3 is the one of the eigenvalue. So next, here 0, here 15 plus 15 we need to get. So here 1. So we need to put here, I'm going to put again minus 3. So 1 into minus 3 is minus 3. So minus 2 plus minus 3 is nothing but minus 5. So minus into minus plus 3 into 5 is plus 15. So minus 15 plus 15 equal to 0. So the another eigenvalue will be 5, here 0, here 1. So here we need to get plus 5. Then only we will get 0. So that means 5 into 1 is plus 5, will get 0. So the corresponding eigenvalues for that matrix is lambda equal to 5, minus 3, minus 3. So that means here we are getting minus 3 two times. That means two eigenvalues are equal. So we are going to find eigenvector for this eigenvalues. So before going to find eigenvectors, we need to consider let x be a any column vector be an eigenvector for corresponding to lambda. So by the definition, A minus lambda I into x equal to 0. So put A matrices minus lambda into identity matrix into x equal to 0. So we'll get this matrices. That means lambda into I is nothing but only diagonal element will come. So we need to minus those lambda into diagonal element. So after minusing diagonal, we'll get this one. So this is nothing but A minus lambda I, this is x, and this is 0. So now we can go and find the eigenvector for eigenvalue. So first I am considering lambda equal to 5. So for lambda equal to 5, we are going to find eigenvalue. So first substitute lambda in equal to 5 into this A minus lambda I into x equal to 0. That means A minus 5i into x equal to 0. We will get this matrix. So after getting this matrix, product first row with this column matrix, second row with this column matrix, and third row with this column matrix, we'll get these three equations. So we need value of x1, x2, x3. For that, we need to solve these three equations. We need to get value of x1, x2, x3. For that, we are going to use method of cross multiplication. To use method of cross multiplication, we need to get two distinct equation. So I'm going to consider the first two distinct equations. So x1, x2, and x3. The same process as last example. So start with coefficient of x2, 2, minus 3, minus 7, 2. So second equation, minus 4, minus 6, minus 4, minus 6, 2, and minus 4. So we are starting with the coefficient of x2. We need to end with the coefficient of x2. To get x1 value, we need to take determinant of this one. To get x2 value, we need to take determinant of this one. To get x3 value, we need to take determinant of this matrices. See here. So here they took the second equation and third equation. So they get these values. So consider this one. So now what we need to find x1 value, take a determinant of this matrices. So product of main diagonal minus product of opposite diagonal. So minus 4 into minus 5 is nothing but plus 20, minus of minus 2 into minus 6, that will be plus 12. So 20 minus 12 is nothing but 8. So see here, here minus 1 into minus 6 is plus 6, minus of minus 5 into 2, that will be minus 10. So minus into minus plus 10. So 6 plus 10 is 16. So the x3 value is minus 2 into plus 2, that will be minus 4, and minus 1 into minus 4, the minus of minus, that will be plus 4. So minus 4 minus 4 is minus 8. So take common values out, we'll get 1, 2, minus 1. So this is corresponding eigenvector for lambda equal to 5. So next we are going to find eigenvector for lambda equal to minus 3. This is lambda 2. So lambda 2 equal to minus 3. So substitute lambda equal to minus 3 into A minus lambda I into x equal to 0. So that is our first equation. If we are substituting lambda equal to minus 3, we'll get this matrix. So from this matrix, take first row and the column vector, multiply, we'll get this equation. So multiply second row and the column vector will get this equation. So multiply the third row and this column vector will get this equation. So see all these three equations, both are same. So the first equation, if you are multiplying 2 with the first equation, we'll get the second equation. If you are multiplying minus 1 with the first equation, we'll get third equation. To use to finding this solution, we are going to use cross multiplication method. But to use cross multiplication method, we need to get two distinct non-zero equations. But here we are having all three equations are same. So that means the only one valid equation. So here only one, we are getting one distinct equation. So but here we are getting lambda is 2. So minus 3 and minus 3, two same eigenvalue we are getting. So to get eigenvector for this two value, we need to get two eigenvector. So for two eigenvalue, we need to get two eigenvector. For that, I am going to consider any of this arbitrary x1 or x2 or x3, any one equal to 0. So here I am going to consider x3 equal to 0. So if we consider first x3 equal to 0, so since two of the eigenvalues are equal, from above equation we have to get two eigenvector by assigning arbitrary value for two variables. So first I am going to do x3 equal to 0. So if we are giving x3 equal to 0, we will get x1 plus 2 x2 equal to 0. So here consider x2 equal x1 equal to minus 2 and x1 equal to 1, we'll get this equation equal to 0. So that means x1 minus 2, x2 plus 1 and x3 equal to 0. So next we need another one more eigenvector. For that I am assuming x2 equal to 0. So if we give x2 equal to 0, we'll get x1 minus 3x3 equal to 0. So solve this equation. To solve this equation, I am going to consider x3 equal to 1. If you giving x3 equal to 1, so x1 equal to minus 3 you will get. So you put those two value, will get 0. So that means these values are correct. So x1 equal to 3 and x3 equal to 1, and already we know x2 equal to 0. So this is the corresponding eigenvector for lambda equal to minus 3. So in the summary we can see the eigenvalues for this matrices lambda equal to 5, lambda equal to minus 3 and lambda equal to minus 3. So the corresponding eigenvector for those eigenvalues are given here. So if we are getting three eigenvalues, we need to get three eigenvector. So for 3 cross 3 matrix, we will get definitely 3 eigenvalue. It may be 0 or any value. So for we need to get corresponding eigenvectors. So at last we can see that when all the eigenvalues are same, that means the eigenvalue for this matrices will be all same. So consider these matrices. So first we need to find eigenvalue. We need to consider this characteristic. We need to find characteristic polynomial. To find characteristic polynomial, first we need to form a matrix A minus lambda I. So this is A minus lambda I. So next take a determinant of A minus lambda I. We'll get our characteristic polynomial. So the characteristic polynomial is nothing but determinant of A minus lambda I. If we take determinant of this matrices, we'll get one 3-degree polynomial. That will be our characteristic polynomial. So first we need to find determinant of that 3 cross 3 matrices. So I'm going to use first row. So expand the determinant along with the first row. So first row, first element, delete the corresponding row and the corresponding column. So similar as the last examples. So find determinant of A minus lambda I and the submatrices determinant, substitute those things into back substitute. Then we will get, after simplification, we will get this 3 cross 3 third degree polynomial, that is nothing but our characteristic polynomial. So this is our required characteristic polynomial. The solution of this characteristic, if you giving equal to 0, that will be our characteristic equation. So the root of the characteristic equation nothing but our eigenvalues. So to find eigenvalues, we can use that L method by taking coefficient of this polynomials 1, 3, 3, 1. So here we need to get minus 1, here put 0, so 1. We need to get 0 here. So first I'm starting with minus 1. So minus 1 into plus 1 is minus 1. We'll get 3 minus 1 is 2. So minus into minus 2 is minus 2. So 3 minus 2 is plus 1. So minus 1 into plus 1 is minus 1. So next here we need to get minus 1. Here put 0. So you need to get 0 here. So 1 plus 0 is 1. So again I am taking minus 1. So minus 1 into minus 1 is minus 1. So 2 minus 1 is plus 1. So minus 1 into minus 1 we are getting. So it's satisfying. So minus 1 again the eigenvalue for this equation. So next here we need to get minus 1, 0, 0, 1. So again put minus 1. So minus 1 into plus 1 into that will be minus 1, 0. So our corresponding eigenvalues are minus 1, minus 1, minus 1. See here all the eigenvalues are same. So next we are going to find eigenvector for this all same eigenvalue. So that means consider let this x be a any eigenvector corresponding to lambda. By definition a minus lambda into x equal to 0. So put a matrices minus lambda into I, will get this matrix. So to find eigenvector, first substitute lambda equal to minus 1 into a minus lambda I into x equal to 0. So after substituting lambda equal to minus 1 into that matrices, we will get this matrices. So after that, product first row and with this column matrices, second row with this column matrices, and third row with this column matrices. By producting, we'll get this three equation. See this three equation. So first equation and the second equation is nothing but 2 into the first equation. So the last one same as the first one. So that means only we are getting one distinct equation. So to use cross multiplication method, we need to get two different non-zero equation, but we are getting here only one equation. So we can't use here the cross multiplication, but we need to get value of x1, x2, x3. But here all the three eigenvalues are equal. From the above equation, we need to get three eigenvector for from this equation. For that one we are going to assume the x all three values are some arbitrary values. So first I am going to choose x3 equal to 0. So after that I will choose x2 equal to 0. So after that I will choose x1 equal to 0. So by assuming first x3 equal to 0, we will get this equation 7x1 minus 6x2 equal to 0. So here what I'm going to do is, if I take x1 equal to 6 and x2 equal to 7, I'll get this equation equal to 0. So we got the value of x1, x2. So that means x1 equal to 6, x2 equal to 7 and x3 equal to 0. So next I'm going to assume x2 equal to 0. If I am assuming x2 equal to 0, I'll get 7x1 plus 5x3 equal to 0. So I need to get x1, x2, x3 value here. So for that I'm going to assume x1 equal to 5. If I take x1 equal to 5 and x3 equal to minus 7, this equation will become 0. So that means x1, x3 are solution of this equation. So I got my second eigenvector. So to get third eigenvector, I'm going to assume x1 equal to 0. So if I put x1 equal to 0 into our equation, we'll get minus 6x2 plus 5x3 equal to 0. So here if I take x2 equal to 5 and x3 equal to minus 6, this equation will become 0. So that means the value of x1, x2, x3 is nothing but 0, 5, 6. So these are the eigenvalues, the given matrices, and these are the eigenvector for corresponding eigenvalues. So far we have seen the definition of, so first we have seen definition of eigenvalues and eigenvectors. So next we see the process of finding eigenvalue and eigenvector. So in the process of finding eigenvalue and eigenvector, first we need to find the characteristic equation. characteristic polynomial. So on the next step, we need to find characteristic equation. So after that, the root of the characteristic equation is our required eigenvalues. After that, using definition A minus lambda I into x equal to 0, by substituting lambda values here, we will get the corresponding eigenvector for the eigenvalues. So these are the some examples. So first we see if all the three eigenvalues are different, how to find eigenvectors. And the second example, we see if any two eigenvectors are same, how to find eigenvectors. And the last examples is nothing but if all the eigenvalues are same, so how to find eigenvectors. So thank you.